really happy and honored to have Professor Levent Degertekin from Georgia Tech to come here to present to us his recent research about CMOD and CPOD. Right?
You have to find a name.
Right.
So.
Levent is a pioneer in our ultrasound community. Many of folks here, ultrasound researchers here in the room, we know he has years has done tremendous, very high quality or excellent findings in the ultrasound community. Right? Levent received his PhD degree in electrical engineering in 1997 from Stanford University, and he recently holds the G.W. Woodruff Chair in Mechanical Systems and a professor at the G.W. Woodruff School of Mechanical Engineering and the School of Electrical and Computer Engineering in Georgia Tech. His research interest has been micromachine, ultrasonic, and optoacoustic device integrated system for medical ultrasonic imaging, bioanalytical instrumentation, and atomic force microscopy. As a very productive scholar with over 60 US patents and over 140 journal publications in these research areas. And on top of that, he has been very successful in translating some of the, those innovations into startup companies. Dr. Degertekin is an IEEE fellow. He's also an associate editor of the IEEE Sensors Journal and IEEE Transactions on Ultrasonics, Ferroelectrics, and Frequency Control. Has won numerous awards, one of the early NSF Career Award, and his paper won IEEE UFC Society Award in 2004, and he is the inaugural IEEE UFC Society Carl Hurst Ultrasonic Achievement Award in 2014. With that, let's welcome Professor Degertekin.
Thank you. Thank you for also being very patient, because this was supposed to happen in March 2020, so like 2.5 years later. And thank you for the patience, and thank you for showing up. So yeah, today I'll be talking about just some disclosures. I'm involved in like 3 companies at this time with some mechanoporation-based cell transfection, imaging, and Xanter does cardiovascular devices. So today, actually, I just want to go over two main topics. One is CMODs. So these are capacitive micro-imaging transducers, and focusing on mostly the area that we have been working on, which is intravascular ultrasound imaging and intracardiac ultrasound imaging. And then move on to more like fundamental transducer research, which we call CPOT, capacitive parametric transducers. And this actually came out of an idea I found actually in my Circuits 101 book. It was interesting because we wanted to make some capacitive devices without a DC bias. How would they work? And it turns out that parametric resonance was an interesting idea to go. We started there, and then it turned out that we could do several different things with that kind of idea. And I also just added a couple of slides for our recent projects, so that with the other faculty members that I'll be meeting later on, we can find out maybe collaboration opportunities. So in general, if you look at the needs for miniaturization and integration and ultrasound imaging, if you, for example, think about an intravascular ultrasound catheter, we're talking about small devices going into arteries in the order of millimeters. So you have to pack quite a bit of functionality in a millimeter-sized device that goes into the arteries. Or if you look at actually your phones today, Qualcomm has, actually, half of the phones use ultrasound-based fingerprint technology to detect your fingerprints. So those things require a lot of, in the order of thousands of elements in a very small volume. So you have to really integrate some ultrasound technology with electronics to be able to kind of do those kind of imaging applications. And then the traditional piezoelectric technology of getting ceramics or crystals and dicing them and connecting them with most glue kind of thing doesn't really work. So you have to use some integrated technologies for these. And today I'll be focusing on catheter-based imaging is one of those areas that you need miniaturization and integration. So again, if you look at, so why do we need catheters in the first place? with ultrasound is that it's the problems with clogged arteries is a huge problem. And what would happen is, though, for example, this is an angiogram where you get an X-ray in real time of your arteries, especially coronary arteries, and you see a narrowing there. But those images only show you where the blood is flowing. It doesn't tell you what's happening on the wall, okay? And it turns out that, especially, for example, women have very different kind of wall characteristics than men. And it may be that blood may be flowing, but there's some problems have started because actually the human body adjusts to those kind of things. But after a while, it gets worse and worse, and you get basically very, very large narrowing. But then you need to know, is the narrowing due to like a fat kind of tissue, or it's calcification? So those kind of things require mechanical kind of imaging. So one way of doing that is basically putting these small catheters and like a radar bouncing light on and off, and then you can get images like this. In this case, for example, there's calcification. So this is the center, and you're getting cross-sectional images in this case. You can see calcification is blocking ultrasound. So from that, for example, the doctor decides even which tool to use. Is it full calcification? Can they break it or not? So those kind of information comes from a mechanical imaging device. So again, for these things, you're looking at 1 to 1.5 millimeter diameter catheters in the 20 to 40 megahertz range. And you want those high frequencies because your resolution increases with frequency. Okay, wavelength comes down, so you want to go higher, but you cannot do that from outside because ultrasounds get attenuated very fast at high frequency. So you cannot just put a probe outside the part. That's why you have to go inside, because you only have maybe 2 to 3 millimeters imaging depth. So if you look at the current IVUS catheters that are on the market, there are two types. One is a single element system. So in this case, actually, you have a single piezoelectric device, and then it rotates really fast, actually 1800 RPM. If you take it actually out of the patient, you can hear this kind of sound. So it's rotating, but it's in a sheath so that it doesn't really touch the body. But for this thing to work, you have to put saline between your transducer and the tube so that sound can transmit through. So it actually gives usually better images, but people actually use mostly this array technology. And array technology is actually what got me into this business, because in even 1990s, they were able to put 64 element arrays, like think about my fingers wrapped around, and then they put 4 or 5 silicon chips to connect to each one of them. So you can imagine there are like around 250 electrical connections made in that small volume. And the nice thing about that is you don't need to rotate it mechanically. With a phased array, you can rotate your beam electronically. So this became a big seller because it's just easy to use. But the problem with that technology is that usually it's limited to lower frequencies because making those smaller piezoelectrics wasn't very feasible, and it's still not actually very feasible. But in both cases, though, what you're seeing is that you go into the artery and then you get a cross-sectional image because they're looking sideways, right? But in many cases, like it's a typical operation, angioplasty operation, you go in and then you look at the artery, and then first you may want to just do a balloon. So you just go in, you inflate a balloon, and then pull it back and see if the artery is still remaining open. But sometimes it doesn't. So what you do is then you go into a balloon and a mechanical stent, which is basically first small. You go in and then you extend the stent, and the stent remains open. So what you want to do ideally is basically to be able to monitor that thing. Because right now, IVUS is used after the fact. Because you cannot see forward, you cannot guide the operation, right? You just do the operation, then you put your catheter back in, you pull it back and forth to see if it's working or not. So, and that's a huge deal, because in cath labs, every minute is money or time, whatever, so they don't want to put an extra catheter in and out. If you can actually guide the intervention and in the first run, that's an advantage. And in some cases, you have this chronic total occlusions, so basically you're blind if you're not seeing forward. So there is definitely a need for imaging in front of you and also generate a volumetric image. So if you can do basically a forward-looking ultrasound device, you can basically have like a flashlight in the arteries. Because actually, one analogy is that you're driving, right, but you're driving looking sideways. Is basically what you're doing right now. But you want to have a windshield, right? So that will give you the front view. And for example, in situations, this is called like a jailed branch. So if you put a stent, but you want to see, for example, there, it's very difficult to do it with a regular IVUS. So that was actually our motivation. So can we basically put a small chip maybe at the tip of a catheter so that we can generate those images? And people have been looking at this as well with different technologies over the years because it's a useful technology for guiding lots of different interventions. So these are some earlier work, like 2003, 2009. But again, these technologies are pretty difficult to put together. Just manufacturing it is an issue, and it's done by hand. If you don't have electronics in there, you have to deal with lots of cables, and that creates yield issues and stuff like that. Those are all actually pretty large barriers for commercialization and broader use of these types of technologies. So again, that piezo technology has some limitations. Also, as I said, like if you have all these elements in there, so you need maybe hundreds of elements, then you have to connect them to a system, right? So, but you cannot, for example, so in a transducer, you have an array, but the ultrasound imaging system is pretty complex because you have to generate some high voltage pulses, and then you sometimes you need to time them so that you can send energy to left and right, or you can focus it, and then you have to have a pretty low noise receiver because the signal that comes back is not very high. So you have to digitize it and beamforming, do all the calculations to get to your image. So usually, basically in the regular cart-based systems, you only have the transducers there, and then that thick cable comes back. For example, if you need 100 elements, you don't want to deal with 100 cables in that catheter. So you need to put some of this system back into your chip so that the number of connections coming out is reasonable for a catheter. So then you need a couple of things. One is a transducer technology and also an integration kind of method and system development. So for the transducer aspect, what we use is this capacitive micro-machine transducers called CMATs. Basically, they are capacitive devices. You basically have a silicon, say, wafer, and on top of that, you build a drum head, which can be in the order of, say, 5 to 150 microns in diameter, depending on the frequency. So by changing the drum head, if you think about a big drum head, right, like a meter diameter, it resonates at 1 kilohertz. So if you want that to go up to, say, 40 megahertz, you may just make that drum head, say, 10 microns, 15 microns, and thin enough, and then that gives you those ultrasound frequencies. And what you do is you apply a DC bias, and then on top of that, AC bias to basically transmit a wave, and as a receiver, it basically acts like a microphone. So you have some charge, and when capacitance change, you get an output voltage. So the advantage of this technique is that you can actually build these things using standard lithography techniques, semiconductor processing. So you can go down to microns, and you can pattern different patterns. You're not limited to dicing, for example, of certain shapes. So over the years, I mean, we have done, and lots of groups also have done, devices from 50 megahertz, 6 megahertz. So you can actually have a huge freedom in that. And the other thing is, this is really suitable for electronics integration, which becomes a key for later on work. So if you look at, again, as an electromechanical device, you would basically look at this basic electromechanical equivalent circuit, and this turns ratio is important so that it tells you how much force you get for a given voltage that you input the device. And for a piezoelectric device, it's basically given by these material constants. And then if you look at a PZT5H, a standard piezo material, these are the numbers. But then to get to those kind of transformer ratios, you need, for CMAT, you need to apply like 100 volts over maybe 100 nanometer or 1 micron gap, okay? So it's not an easy task. You have to put lots of electric field on that material. So then the key development in this technology was development of good dielectrics and also being able to evacuate those cavities so that you don't have arcing. Because this idea was more than 150 years old, but they couldn't make them before because they couldn't evacuate cavities and they couldn't make strong enough, small enough membranes to sustain that kind of force. So that happened around 1995 or so, and that's where this CMAT field came about. So this is a simple model, but in order to build reasonable devices, you have to put many of these membranes together. So what happens though, think about this, right? If I have a membrane, if that moves up and down, it actually pushes the fluid to the left and right. So this actually creates crosstalk. I mean, ideally, if I have an array of devices, when each one moves, I don't want any other to move, so that they're independent array elements, right? But this may not be the case. So this is like a pretty bad case of crosstalk, because I'm exciting this two membrane rows, but the sides are already also moving out. So that doesn't really work as I want. However, though, I mean, we developed methods for that, especially because of the fact that the forces that we apply in these devices are nonlinear forces. So electrostatic forces go with the square of a voltage, meaning that you put omega 0, but mostly 2 omega 0 comes out. So you have to really have a good nonlinear model. And for that, we actually use the Simulink to develop that model so that we can predict large signal, so when I actually swing the membrane a lot, versus small signal when I'm just receiving a small vibration. So that we have the full capability of designing these devices, because without a model, you cannot really predict and design high-performance device. So with that model, we were able to actually predict, for example, this should be the pressure output at a certain distance, and this is the measurement, and we can actually fit the curve on it. So we are now able to, after around 10 years or so, we had a good model to predict the complex behavior of this type of device. So with that one, now we can go ahead and design devices. So also let's talk about the integration aspect. So we basically have, you can actually integrate things with wire bonding, but when devices get so small, in the order of 20 by 20 microns, the capacitance is so small, even the wire bond capacitance can be larger than the device capacitance itself. So that's why you need to do integration and connect your amplifiers as close as possible. So that reduces your number of connections from maybe 200 to 10 to 15. So these are some devices that we have made. So this is what you do is you design your electronics first. And this, for example, device has over 100 elements. So there's a transmitter, receiver for each of those elements. You get your electronics designed first. Then you fabricate membranes on top of it. So this is the monolithic technology. And then you basically have a device. This is quickly what happens. So you get a wafer designed with special electronics. You then get your connections. So those are the connection points. And then you make your membranes, and all those membranes are connected with the electronics in a very short distance. So, and also, we are not really pushing any limits. If you look at the structures actually underneath the CMOS structures, are there at least an order of magnitude smaller than what we are doing today. So you can really make things smaller if needed. And then you can actually shape these things using some micro machining techniques. So you can make holes in them, you can make them round. And then basically more or less a pretty large system can fit in your, on your fingertip. So in that device, for example, we had integrated the transducers, the transmitters, and some of the amplifiers. And then this device, if you put it in an artery, this is what it would see. Basically, you're going in an artery, there's a wire in there, there's a stent, there's a side branch. So you can generate all these three-dimensional images using this device, right? And actually, it took some doctors like 2 years to understand this image. That yes, oh, I'm not putting things down, I'm just looking in front of it. Because they're just used to seeing the cross-sectional images. So these are some real data for a stent, for example. So you put a stent in front of that chip, and you can actually map the stent struts in 3 dimensions. And then actually we put real a chicken heart in front of it, so that we want to show that we can go through tissue with all the attenuation and see maybe a centimeter deep. So this is, for example, the apex of the heart, and then you're looking at different cross sections. So this actually shows that this technology would really work in real life. So for further integration, we also looked into intracardiac imaging. And in intracardiac imaging, you basically put a larger catheter in a larger artery, because instead of the coronary arteries, you're looking at the valves and the structure of the heart. And this is basically a commercial, now commercial piezoelectric device. And then even in that case, you have to put electronics underneath, because you have 1,000 elements there. Okay, so to come up with say 100 cables, you have to get your piezoelectrics, some other matching material, an ASIC, and 7 layers of interconnect. Okay, so that also is very complex. So this catheter will probably cost like $10,000 to $15,000 to sell. So if we can actually integrate things, we can get all those layers down to a single layer and a single chip device. So actually, we did that. So we're seeing a 1D array in this case. And to reduce the number of cables, so this is before, this is the CMOS, and then after, this is after we make our devices on top. And then what we use here was like 8x1 time division multiplexing. So we get 8 channels, but we sample them very fast and put it on a single cable. So that's how we were able to reduce the cable count by 8 times. And in this case, for example, we were able to put some of the transmit beamforming also on the chip itself. So our latest work is actually, we did more of that. We put some of the receive beamforming, we call it. So we get the signals from 5 elements together, and then we phase them, and then add them up, and then afterwards do the time multiplexing. So 5 times reduction in those small arrays, and 8 times reduction in time division multiplexing. Then actually, then you show 40-to-1 reduction ratio, meaning that you can have 1,000 elements in there, and you come out with only 25 cables, okay? And actually, cable cost is 30 to 50% of the cost of a probe. So just, I mean, to me, it was interesting because when I told this to the companies, they were more interested in the cable count reduction, the cost reduction, than the technology itself. Oh, okay, we can make more money, so that's fine. But with that one, we actually added a little bit more of receive beamforming there. So you're putting most of your ultrasound system into a chip. This is the commercial device now that's available. It's a handheld ultrasound device that works in a very large frequency range, so that you can look at the fetus, at the same time your heart, at the same time your carotid artery with a single probe. And this is, to me, like again a feat of technology, because there's 9,000 elements in there, and then each element has an amplifier, and everything is digitized in that probe, and you just connect your iPhone, and then you can get an image. And actually, what's interesting for this one is that it can do 3-dimensional imaging. So you can put it on your body, and then it can scan in 3 dimensions, for example, give you a bladder volume. If you think about it, I mean, there are specialized ultrasound probes just to measure bladder volume, and this one does it in addition to all these other things. So, and the importance of this is that one of the biggest hurdles was creating manufacturing technology. Because you can have a great idea, but if it's not manufacturable in large scale, you don't really much have a chance of a commercial success. So after a couple of $100 million, they were able to do that, but then that now opens up other applications. Once that's done, you can basically scale this technology for other applications. So that's basically more or less what I want to talk about on CMAT. So it took 20 years. Now the products are coming up, and there's still opportunities, and mostly limited by, I would say, the business decisions of people that getting this technology more into the market. So one thing that I mentioned, so I'm switching to our parametric device now. So, and the question that we asked was this. So for the CMAT to work, we have to apply a DC bias to put a certain charge for that to move, right? But if you wanted an application where you're trying to charge a medical implant in the body, you don't want a battery or charge initially, right? You want a totally passive system that you can send energy to. Like RF links are used like coil to coil. So, and that's a problem. With the piezo, you can do that. But can we do it with a capacitive device? So that was when I looked at my Circuit 101 book, really. And like 30 years later, you understand things better, a little bit better when you read the same thing. So apparently, I mean, it can be done if you use what's called parametric resonance. So actually, parametric resonance idea comes from something like this. So if in the playground, so if you just get some started, right, what you do is you basically swing your legs, for example, you shift your weight at 2 times the frequency of oscillation. So you actually input 2 F0 to the system, but the system actually moves at F0. So that's basically parametric amplification. So, and that has been used in electronics as well to amplify signals, because it has the chance of amplifying things without adding noise. So that was important for them. So now, basically, it turns out that if you just have some energy from the thermal energy around the environment, if you can ultrasonically move that that device at 2F0, it can actually, you can start pumping energy to it. So it becomes a very simple circuit. So this is your capacitor where the plates can move up and down, and you make it a part of an RLC circuit. So this circuit has a resonance of F0, and then what you do is you wiggle that capacitor at 2F0. And what happens is, so this is in time, you basically start pumping energy. So when the charge is exactly 0, you basically increase the capacitance. When the charge goes up, you decrease the capacitance by opening these things up. So the mechanical part of the energy, that vibrating membrane, does that. And then if there is an initial voltage there for some reason, then basically it starts building up. And it turns out that if the capacitance change, which is delta C over C0, is larger than 2 over the quality factor of your electrical circuit. So the nice thing is that you can control the quality factor of an electrical circuit by basically just with a low loss inductor and low resistance, you can do that. And then if the change is large enough, actually it goes into resonance. And then it doesn't go to infinity. After a while, it basically gets limited by some nonlinear effect. But you can actually pump energy without no charge in the beginning. So, but again, the key is that all of a sudden you have this electrical circuit that really controls all those thresholds and behavior. So that's a good thing. So basically you have this mechanical resonator coupled to an electrical resonator, and we have much better control on the electrical side to basically determine the behavior of this. And basically it is two coupled nonlinear differential equations, because on the electrical side you have displacement coming in because that's how the capacitor is changing. And on the mechanical side you are applying force to the voltage, so those things are coupled. And it looks simple, but we needed an applied mathematician to solve these problems for us. Okay, it was beyond our capabilities. But we could use Simulink. Right, so you can always simulate numerically. So we did simulate this kind of behavior, and that's what simulation told us. So if I send ultrasound at 2F0, and then I just apply a ping to my circuit and see what happens in the electrical signals. If the ultrasound is not strong enough, I ping it and it kind of wiggles and then dies down because there is no energy coming in, right? But then if I turn the ultrasound, then I ping it, and after a while, it starts going up and up and up, and then actually it sustains continuous energy. So it's a totally passive device. I don't because that initial ping can come from thermal mechanical noise in the system. So I don't really need to put energy in the system. As long as it's non-zero, it basically picks it up. So this is our initial experiment where we kind of had the receiver. We just made an RLC circuit with a transmitter. And then when we send the signal at 2F0, and then we block the ultrasound, so the circuit kind of does its thing and it decays. But then when we remove the ultrasound barrier, it basically goes up, and then it sustains the oscillation. And it depends on the level of oscillation depends on the ultrasound. So it either dies, or if you're above the threshold, you can get power into the system. And actually, we did a more complex thing because it's not easy to have a single transducer, single capacitor at frequency of interest. So we go back to our CMATs. So we make the same kind of device, but without any bias connection. We still have electrodes, but we don't need to apply bias. It gives you complex behavior. But I mean, at a certain point, you can actually get more than 20% efficiency from input ultrasound power to your output. And on top of that, it's not very useful to AC because you have to turn it to DC for energy harvesting or charging a battery. So then we added actually some diodes to the circuit and a full bridge. And then with that, we were able to actually get milliwatts of power from this system. And if you use a switch, you can actually get up to 60% efficiency from the input power that you deliver to the DC output. And to do that, what you do is because you first need to build it up, enough voltage to turn on those diodes, right? So that we cannot do in the beginning. So we just do it first without a diode. You just get the energy, and then so that we can start using a switch. Then actually we turn the switch, and then it starts going on by itself. One critical thing, though, is that, as you will see here, this threshold, right? So for example, this is the load that I use, that resistance, because as I said, that threshold depends on the losses in the system. So if I make my load very high, it basically stops oscillating. Okay, the losses in the system is too high. But that abrupt transition actually is a good thing. For example, if you're trying to make a sensor out of it, right? If you want to sense that load, all of a sudden it jumps. It's like a digital sensor for you, okay? So that actually was interesting. And we actually use that for energy harvesting. So now a couple of things as well. Again, that transition. So it's interesting to me is that it really led to all these different applications that we haven't really thought about in the beginning. So for example, if you think about vibration control, so more like mechanical engineering, right? So if this is the response of a microphone that you have, this is not a very good microphone in the sense that it has good sensitivity right up to 10 kilohertz, but then it has this sharp resonance, right? So which means that it's going to ring a lot. So what you would do is you would find a mechanism to damp that resonance so that you have a nice flat response. So how do you do that? Usually you use an active or passive means. Active means you detect it and then you provide the signal back so that you keep that vibration constant, right? The other one is you actually put lots of damping to the system, so you reduce the quality factor. But what happens is when you add damping to the system, you actually introduce noise as well. Because this fundamental thermomechanical noise says it's 4 kTr, R being your losses is the noise. So ideally, you don't want to introduce noise to your system while you're damping it. So that's when this thresholding becomes important. Because now let's look at the system. So we have our device. This is regular your mechanical device with damping. You just connect that to, an L and R, okay? So now this capacitor, and that becomes our parametric device. So what would happen here is that your device starts moving. It moves fine. But then as soon as it goes over a threshold, right, then the parametric resonance comes in and it starts damping it. So as long as the device motion is small, it doesn't do anything. But then as soon as you get to that high peak, it basically damps it automatically. It's really like a passive system. I didn't do anything. I just put that LNR there. But you choose those parameters judiciously so that at a desired level, it automatically comes into, gets into action. So for example, in this case, while the device is moving, but it's slowly building up the voltage, at a certain point, it goes into parametric resonance and it damps the response. So again, so we can simulate this with different quality factors. So again, just playing with the electrical properties, I can basically, so for example, this is the response, it comes in, it only starts acting at a certain point, at that threshold. So if your input is in this frequency range and large enough, it basically damps it. But after that, it basically goes back to its normal state. So in a way, we basically damp the system. And in this frequency range, we are not doing anything, meaning that we are not adding noise to the system, right? During that range, it's fine. But then when it goes above a certain threshold, it basically damps it automatically. And you can control how much damping you have by adding some electrical voltage if you wanted to. So this also, we showed it experimentally. This is again a membrane array. And then we are exciting things with a piezo at the bottom. So we are vibrating the system from outside. We are not applying our own signal. And then using a laser vibrometer, we're looking at the vibration of the membranes. And then we do, let's say, a frequency sweep. And then we see that, like, this is the membrane displacement. And then this is the voltage. So at first it goes up. But after a while, when it goes to that threshold, it damps down. And the voltage in the system goes up. So what happens is your mechanical oscillator works. Only at a certain threshold, energy gets transferred to your electrical side. Okay, and then you can adjust that electrical threshold by, again, designing your electrical system. So again, this student was very curious. So he said, okay, what else we can do? Because when you have a nonlinear system, and this is the first time we kind of like nonlinearity. Usually in transducer world, you don't want nonlinearities. We want to stay away from them. But one interesting thing is that people use these nonlinearities to generate these extra frequency components. Because that's what nonlinearities do. You just put in one frequency in a linear system, you put one frequency in, the same frequency comes out. In a nonlinear system, you get these different ones. usually they're in the harmonics. But then people found out that in addition to harmonics, you have all these frequency combs that come out. And actually, they did it in optics first, and that got a Nobel Prize for them. And the nice thing about these frequency combs is that you have this coherent, very closely spaced frequencies. If you think about like taking a Fourier transform, you can sample your Fourier domain very, very, very finely with that. So, I mean, if any of you had done like phase unwrapping, so you would find the problem that if you don't sample your frequency fine enough, there may be 2 pi phase shift and you lose your information. So they actually started using this so that they can sample the frequency very nicely. And then people did that in mechanical domain as well. But for that, what they had to do was they needed like a mechanical resonator in vacuum, and they had to adjust the higher order modes of the system so that you put energy in one mode of the system, parametrically it couples to the higher order mode. When that goes going, actually it couples back, and those interaction creates those combs. So it was pretty limiting in terms of what you can do with just purely mechanical systems. So, okay, it looks like the same thing, right? So we basically, again, if I couple my mechanical resonator to our electrical resonator, and then if I, for example, drive that system, it can be 2-tone or a single tone. It turns out that actually the interaction between these two resonators also create combs. But again, the nice thing about that is I can control the quality factor of my electrical side independent of my mechanical side. And there are actually many applications where you may not want to have a very high quality factor mechanical device. For example, when I immerse a cantilever or an oscillator in fluid, it gets damped, right? But I want to make a sensor in the fluid. I want a damped mechanical resonator, but still have this kind of nice capabilities. So that's basically the catch basically here. And again, if you look at the equations, the same couple equation, you can be driving it with a voltage or with mechanical force. Basically, pushing it in one side creates some frequencies on the double the frequency. When this thing gets high enough, it basically couples back. And then that coupling creates basically some slow modulation. And that slow modulation basically gives you that comb action. So basically, this is what we did in air. This is a commercial like CMOT device that we were able to get. So again, we're just driving it in an RLC circuit. So if you drive it, for example, at around, say, 1.3 megahertz, and if you look at the voltage, we start seeing this kind of waveforms. Basically, this periodicity in time gives you periodicity in frequency domain, and then that gives you the combs. So we were able to generate combs, and the most interesting part of this slide is that when we increase our drive, actually the comb spacing was changing, okay? Meaning that somehow, if something changes in the mechanical domain, which changes my vibration, actually it's going to be detected, it's going to change my comb frequency, right? So, and then the other thing is that how sharp are these peaks? Because you want the sharpest peaks, so that you can differentiate things. And the sharpness of the peaks depend only on how long you digitize the signal. It doesn't really depend, in this case, on the mechanical or the losses in the system. So those are two main advantages, okay? So then, this gives you the idea that, okay, if I can find a way of measuring that comb frequency, I can actually make a sensor, a mechanical sensor. And our mathematician had a model. And so this is basically like the critical forcing. This is the mechanical loss in the system. This is the electrical loss in the system. So if the system is lossy, you need to really push it really hard to generate those combs. However, though, if your electrical quality factor is high, so if electrical losses are small, you can achieve that kind of comb generation at a lower force. And it's interesting also that, for example, that theory predicted that the delta comb frequency would go up and then come down with certain application of voltage. Actually, we see the same thing in the experiment as well. It's not a pretty simple mechanism, but it's somewhat predictable. So one thing then, okay, how do we get this higher quality mechanical resonances in fluids? in liquid state. I mean, in air, we are able to do it because in air, the damping is small, right? So the way to do that in a fluid environment is that you can create another resonator. For example, if I put my transducers, right, and then if I put a hard wall, then energy actually, I create a second resonator. So if you look at the frequency response of that, you have this broad response. This is, for example, quality factor is, say, 0.6. But in that response, you start getting these sharp peaks. Because of that, the energy actually starts bouncing back and forth in the fluid. And think about this. In a microfluidic channel, you have transducers at the bottom and you have a top. Right? You start sending energy up and down. That creates some high-quality resonances in liquid, right? So with that one, and then by connecting it to our resonator, so we were able to generate combs. And apparently this is the first ever demonstration of like mechanical comb generation in a damped environment. So we used kind of our mechanical resonator understanding and electrical resonator understanding. When we put them together, you can basically see that by changing your drive, you can change the comb frequency again. So with that, you can, like, I think we had the simulations of if you change the density of the fluid, other properties, you can actually detect it looking at this comb. So this can actually lead into a new type of sensor device that you can integrate into different things, because we know that we can integrate electronics, we can integrate transducers, and then you can just build microfluidic channels on top, and then you have a new type of device. So this was pretty interesting for us. So I have a student who is actually trying to, as a postdoc at Stanford, he's trying to apply this to biological biomicrofluidic systems and see what he comes up with. Now, so that's basically the end of that parametric device and applications part. So these are some of the projects that I wanted to mention, what's going on right now. One sensor that we are developing it's an acousto-optic sensor for like guiding interventions under MRI, for example. And the issue is that when you do interventional MRI, you actually, again, put catheters inside the body, and you want to know where the catheters are, okay? So how do you get the location information? Today, they basically just put a coil, and in MRI, as soon as you detect the RF signal, and if you look at the frequency content of it, that gives you the location information. But if you use a regular cable, what happens is that at those frequencies, those regular cables electrically start resonating, and they heat up. Okay, so you don't want to use conductors, because you can assume that it's like a microwave oven in a different sense, right? You don't put metals in a microwave oven. So now the idea was, can I basically get that signal without disturbing the field and without getting hot? So then we basically started using optical fibers, because optical fibers are dielectric, they don't get hot. But then you can put a receiver. Actually, the receiver can just be a piezoelectric device, because a piezoelectric device sitting in air, if there's an electric field, it starts wiggling, it just gets electric field. And that actually changes the properties of the optical fiber. And then if I bounce light back, I can find out, and that's called Acrostopic Modulation. So we are able to actually get those signals back, and then you can actually locate, and this is an animal study, that you can put this at the tip of a catheter, and then when the catheter moves in, you can actually see the dot moving in 3 dimensions under MRI. So we first did this using basically just slapping a piece of piezo to an optical fiber. It worked, which means that this idea has merit. Because if the first dirty thing works, you probably can improve it. So now we're improving it by using some like piezo material that we can coat around the optical fibers. So that increases the coupling efficiency, and we can control things better. So that's one project that's going on. So I know some people here are working on robotics and MRI. So this actually can help in that kind of application. Another application that we are working on is using focused ultrasound for drug delivery in the brain. So basically, you need to injure the blood-brain barrier to get larger molecules to the brain from the blood. So one way of doing that is you put these microbubbles, and you inject them basically, and they go everywhere, and they go also in the brain. But then what you do is, by ultrasound, you basically start vibrating those microbubbles. And since they're very elastic, they can actually move a lot. So when they move around, they can actually rub against the the arterial wall, and you can injure it, and then molecules can go through. The thing is, though, you should not overdo it, because if you injure too much, or if you burst the bubble, it's a problem, right? So what you want to do is, though, you want to keep it in this region where it's called stable cavitation. So there are two things. One is you want to locate it properly, and you're going through the skull, which is problematic, so we have to talk about that. But then, on top of that, though, you need to make sure that you're not doing too much, right? So then what we do is, though, we use the CMATs as a broadband receiver, because what happens is when these things, microbubbles, wiggle, they generate the harmonics. So you can listen to those harmonics and tell how much they're oscillating, so that in a control loop, we can keep it at the right level. And also, at the same time, we're actually looking at the reflection, so we want to make sure that there are enough microbubbles there, because your signal can go up and down depending on the microbubble density, so you want to kind of calibrate that. So we added that feature to the controller. And so right now, for example, this is being done with piezo arrays, and this acoustic emissions are all done with piezo. We're trying to get into micro machine devices, and maybe also use, because in this case, the amount of pressure you need to get those microbubbles is not very high. So it may be possible to do all of that using these micro machine devices rather than piezoelectrics. So that will be like in the future, maybe 5 to 10 years time range. Another like recent work that we have done is really having a totally wireless ultrasound imaging system, so that, for example, wearable ultrasound, so you can charge it, and then you get your data in and out. So it's a pretty kind of large chip. But in this case, the idea was to put this under the skull. After an operation, for example, you remove the tumor, and then you want to see how that dissected area is behaving. So you can do that with MRI, which is very expensive and all that, but ultrasound gives you the same information. So then the idea is to kind of put that implanted for maybe a couple of weeks, couple of months, and then power it from outside. And for that, basically, we're using around 40 megahertz transmission through skull. And then this chip does basically everything about imaging, transmit beamforming, receive beamforming, and then sends the data out. And the nice thing about this method is that the imaging doesn't need to be fast, because brain is not moving a lot. So you can have one frame per second kind of rate, meaning that I don't need to be fast and power hungry. So we can just do the slow enough. And actually, we get some images out of this system, which will be presented in the upcoming symposium in October. So to conclude, we talked about the CMATs and CMOT-on-CMOS technology. It's really an enabling technology, and for catheter-based imaging and large arrays. And as I said, the robust fabrication methods are finally available, so commercial products will be coming out more and more. The CPAT structure is unique in the sense that it doesn't require DC bias, but it also led to different types of devices that we can use in MEMS or other ultrasonic sensing applications. And I usually forget this, so these are some of my collaborators, the current collaborators, and funding sources. Thank you.
Time for some questions. Yeah.
Very nice talk. I know it's very challenging to integrate the CMOS and the MEMS devices.
Mm-hmm.
Not even mention piezoelectric. So I guess what you showed is something developing on. Are you aware of any commercially available foundry service provide this kind of information?
Yes, there's a commercial foundry like Philips Innovations. They actually, so the transducers that we used here, for example, these were done by that commercial foundry. And the key is that being able to make these devices at low enough temperatures so that you don't destroy the CMOS electronics underneath. And they have the technology to build those things on CMOS electronics. So and they would work with universities. I mean, this other technology that I mentioned, that handheld probe, they won't allow you to kind of access that technology. The fab that makes it is commercial, but you need to have $100 million in the bank to be able to work with them. So that's a little bit tough. No. But these guys may, like Philips Innovations can may.
great talk. I have a question about integration and how do you reconcile that with the bigger and bigger need for raw data, for AI, for characterization. So especially with the plaque, you want to know if it's calcification or fats. Of course, you can see that in the image, but there's much more that in the future we'll be doing with raw data.
Raw data and fast imaging and all that, right?
But
Yeah.
how do you reconcile that with the need for integration early in the process, because you never work with raw data anymore at this point?
That's a good question. I think you can still do it to some extent. Maybe some of that processing that you're doing, right? You can move it on the chips, on the chip to some extent. Actually, we will be working on that, and also some other things that, like we talked about, like this 40-to-1, right? I mean, say you don't do micro beamforming, but you do some other tricks to reduce the data rate so that you still give the compressed sensing kind of thing, right? So you can compress the data a little bit before sending it out. So that can help. But yeah, I mean that's an issue if you want to get raw data. I mean the time division multiplexing gives you the raw data, but when you start doing the micro beamforming, then you start losing that information. Yeah. Yeah.
My question is about the CPAP. So you mentioned about like it's possible to operate without DC lines or voltage.
Yes.
So like about that the equation, like you need that initial some sort of equal like small voltage, and you say like it's possible for the thermal coupling or some kind of that external noise. So my question is like to get enough output voltage, enough energy harvesting, what's the like initial like pressure input to that device, and like is it lower than FDA limit? Because for human body you need to do the lower.
7.2 milliwatts per whatever millimeter square kind of thing. Yeah, I mean, so actually you get to those levels. The thing with the threshold is that really in all those experiments, we didn't apply any bias. I mean, what would happen is, in this case, like E&M feed through generates something. And if even like when I say thermal mechanical noise, that is very small, right? But it's broadband. You have all those frequencies. What happens is if your initial condition is, say, small, then it takes longer time to build. But again, that long time is in the order of, for megahertz devices, in the order of milliseconds. Then actually it builds up from nearly zero initial condition. Yeah, and also in terms of your, ideally, right, if I can get to like 25% ultrasound efficiency, plus like maybe 50% rectifier efficiency, then then from like 7 milliwatts per millimeter square, I can get reasonable power for an implantable device. Yeah.
Make sure I ask some questions. The first question.
You don't need to, but anyway, I'll take it.
The first about the CPAP Iris, I saw in your array you have transmitter and the receiver. They are separate, not share the same membrane. Am I correct?
Yeah, I mean, and the reason for that is, I mean, at that point, if you use the same device for transmit and receive, then you have to put a switch, and actually that switch introduces noise. Okay, so if you can avoid that, you can have a lower noise system. That was the motivation, and also in that particular case, since we were dealing with rings, we didn't need to fill the aperture. Just having two rings, we did not lose any resolution because the rings are very small, but then you gain in the noise. That's why we actually had separated that dual ring kind of structure. But and actually, that was just really demonstrated because we wasted a lot of area with no electronics, no CMATs. So if I do it today, I would just fill it with membranes, and then we know that we can put much more electronics there. So you can even do transmit beamforming, receive beamforming on that small chip. Yeah.
Any other questions from the public? If not, I can continue. One thing with your CPAP, that tuning, to my knowledge, that tuning is going to the specific frequency.
Yes.
Later on, you can put the code. This is quite different. And I understand you can do sensing, energy harvesting, some especially sensing can benefit from that. But that is not in our images side.
we always want the broadband.
Yeah. So CPAT really is not for imaging applications. It's a totally different area. And like for energy harvesting and those kind of things, actually you like kind of, okay, one thing that I didn't show is that for energy harvesting, you want broad bandwidth as well. And the trick that we did there was we actually added more LCs. Okay, so that you basically have multiple electrical resonators, and then one of them picks up. So then you actually increase your bandwidth that way, if you want bandwidth. But you have to be very careful on choosing those element values so that your loss is not high enough, and then you get into parametric resonance. But for other applications, for like implant powering, you're a single frequency anyway, so it can be good enough. Or you can tune your input to get that energy in. Yeah.
Any other questions?
I have a question about confirmable arrays. I know very little about them, but I think they're very cool.
Mm-hmm.
Do you work on that kind of transducers, and do you have, comments on what are the limitations and?
To me, I think I would like to work on those things because I think this technology is very good for that. And especially, what I'm imagining is that, like your whole wafer, right? Because, anyway, you can have a process where your transducers are made on a wafer, and then you put this polyamide like flex circuit level on top of that, and then you release it, and then actually you have your everything all aligned, at least on that one together. The biggest challenge is how do you know the relative positions of your elements when it's conformal? But you see what I mean for imaging? But I think even that can be resolved because there are lots of cool, actually, ultrasound implant ideas, right? Very simple. And then you can have your array ping something and then optimize it, right? Because with the computational power, I think you can get there. Yeah. But I mean, in terms of manufacturing, I mean, I don't see an issue with like this large, like a wafer level connection. I don't think it's a problem. And with this wireless, I mean, so, you see, I think we have been building up the technology. Like now, if I can do it all wireless, right, then those things become easier.
Yep. Final call for questions. No, really thank Professor Degertekin. We understand 2020 spring, that time, Professor Degertekin is supposed to be here, and then COVID and scheduled time finally got here.
Yes, I'm glad to be here.
And we got really many interest from here. Again, thank you very much.
Thank you.
Thank you all for coming. Hope you enjoyed it.